But back to calculating delta H's. We might get to bomb calorimetry today. I'm just not sure. But we're going to talk about first some rules for using Hess's law with respect to manipulating those thermochemical equations. So Hess's law and rules. We're manipulating those thermochemical equations. So we haven't seen an example of this yet, but we will in a few minutes as we work some more of these problems. If you have to flip an equation, you must reverse the sign. So if, and I'm calling it flip, if you flip or reverse, same thing, an equation, the sign of delta H is also flipped or changed or reversed. So if delta H is positive in the forward direction, and we have to reverse that, it becomes negative. You did see this yesterday. Identical formulas on opposite sides. Of the equation are canceled. So that means they have to be on opposite sides of those arrows. And the third rule is if coefficients are multiplied or divided by some factor, delta H must be treated the same way. Whoops, same. Okay. So we're going to start with this problem. So what you will get, whether it's a homework assignment or an exam type question for delta H, what you'll get is a target equation or the overall equation. Or the overall equation for the process. So for this particular problem, we want to calculate the delta H of the reaction of carbon and sulfur. And remember, I've told you that the form or the phase is going to have a different delta H, so you have to be careful. So the delta H of graphite is going to be different than the delta H of diamond, and I think I showed you that as an example. The shape of this sulfur is also going to impact that, and this is rhombic, and that is the shape. And when these react, we're going to form CS2 liquid. So this is a reaction for 1 mole of CS2, producing that. So what else would that be called? What other type of equation do we talk about with respect to thermochemical equations? Pardon me? Formation equation. So this is both the regular thermochemical equation for the process, but it's also the formation equation because we're forming only 1 mole of this product, and it is being formed from its elements in their most stable physical state. Okay? And remember, I told you you have to be able to recognize a formation equation. And we are given 3 equations to work with. We're given C graphite plus O2 gaseous, which will produce CO2 gaseous. And the delta H associated with that reaction is negative 393.5. And in this column, those are all going to be kilojoules. We're also given S rhombic reacting with O2 gas to give us SO2. And the standard heat of this reaction is negative 296.1 kilojoules. And finally, we're given CS2 liquid plus 3O2 gaseous gives us CO2 gaseous and 2SO2 gaseous. And the standard heat of this reaction is negative 1072 kilojoules. Now, when we apply Hess's law to this problem, we need to manipulate these 3 equations such that we can cancel everything that doesn't appear in the target equation. So this is the indirect method for calculating delta H by using Hess's law. So what we want to do is we're going to look at the first equation. And you want to determine if it's in the right orientation. So what we want to see is reactants on the left, products on the right. And graphite is a reactant, so this one is in the correct orientation. So I'm just going to rewrite that here. How about this second one? Is it in the correct orientation? Do we have a reactant on the left? S rhombic is one of our reactants, but how about the coefficients? Do we have the number of S's we need? No, we don't. Page says no. We have 2 in the target equation. So we have to multiply all the coefficients by 2, and we'll treat the delta H the same way. So we have 2 S rhombic plus 2 O2 gaseous, giving us 2 SO2 gaseous, and my delta H gets multiplied by 2. I'm just going to, oops, oh, I got that all messed up. So it's going to be 2 times that negative 296.1. How about the third equation? Do we have to do anything to it? I hear no, I hear yes. Which is it? Someone is gesturing back there what to do. Flip it. We have to flip it because this is a product. Okay? So we flip this. We don't need to do anything to coefficients because we just have one mole here. So we have CO2 gaseous plus 2SO2 gaseous, giving us CS2 liquid. So what happens to my standard heat of reaction here? It becomes positive. It's negative in the forward direction. I had to flip it, so it's positive in the reverse direction. So now I need to go through and cancel everything but what appears in my target equation. And I have CO2 here and CO2 here. Those cancel. I have an SO2 here and an SO2 on the left. Those cancel. What happened here? Wait a minute. Oh, I missed the 302. Where is it? .302. What did I do there? Oh, over here. Jeez, thank you. Ugh. Okay, so I've got 3O2 here and 3O2 here, so those cancel. Sorry about that. So when I sum these, I have C graphite plus 2S rhombic, giving me CS2 liquid. And my standard heat for this reaction then is just going to be the sum of those delta H's. And when I sum those, I get 86.3 kilojoules.
So when you cancel the oxygen, what happens to the 3?
Well, I've got 3 on this side.
Oh, right.
Yeah, and 3 on the other side, which I failed to put there first time around. Yeah. So endothermic or exothermic reaction? Because delta H is positive. Yep. Yep. Good. Oh, what did I do there? So let's do one that involves some stoichiometry, which we all love, right? We want to calculate the quantity of heat energy that is produced when 4.0 liters of an 85% ethanol solution by volume is burned. And I am told that the density of the solution is 0.7893 grams per mil. What's the first thing I need? Thinking of stoichiometry. I need what? How about a balanced equation? So I'm just going to give it to you. I'm not going to run through the balancing, but you need one. And of course, this is combustion, so we're producing CO2 and water. So we can do one of two things. First, I'm going to actually calculate the standard heat for that reaction using the heats of formation. So this is our direct approach to calculating delta H, which of course involves summing the heats of formation of the products and subtracting heats of formation of the reactants. So our standard heat of reaction, so we have to look up those values. We have 4 moles of CO2. And I looked up the standard heat of formation for CO2. It's minus 393.5 kilojoules per mole. And to that, I'm going to add the 6 times the standard heat of formation for water. In the gaseous state, it is negative 241.8. And again, that's moles. Kilojoules per mole. And then you're going to have to go down here. We're going to do the same for the reactant side. I have 2 moles of ethanol, and we're going to subtract this sum and of its products. Negative 277.7 kilojoules per mole for ethanol. And what is the standard heat of formation of O2 gaseous? Nope. O2 gaseous. 0. O2. That's its most stable physical state. So this is 0 kilojoules per mole. So keep in mind, these coefficients are exact numbers, so we won't consider them with respect to sig figs at the end. But we will consider with the adding the decimals in place. So the standard heat of this reaction is minus 2469.4 kilojoules. These moles are canceling. And I need how many sig figs? Actually, we're good, right? We needed 1 decimal place. So we're good here. So that is heat flow for 2 moles of ethanol. Okay. The question asks us to calculate the heat produced when 4 liters of an 85% ethanol solution by volume is burned. So I need to know how many grams of ethanol is present in that 4 liters. I have my given to start with, which is 4 liters of ethanol solution. Whoops. What can I do here? Am I given a conversion factor? Or how many conversion factors am I given? So this mass percent is a conversion factor and density is a conversion factor. And that mass percent tells me, and this is by I'm sorry, I said mass percent. It's by volume, but you deal with that the same way. That just tells me that 85 mils of ethanol are equivalent to 100 mils of ETOH solution. Okay. If it were mass percent, it would be 85 grams per 100 grams of solution. So I have liters here, so I need to convert those liters to mils. So I can use that mass percent to convert to grams eventually using density. So I've gotten rid of my liters, I've canceled mils of solution. Should denote that so we're clear. And this is mils of ethanol. And actually, let's take no, that's right. Okay. In 1 mil, for the density of, actually this is density of ethanol, I have 0.7893 grams of ETOH. So in 4 liters, I have 2,684 grams of ethanol. This is ETOH, sorry. Does this make sense? So ultimately, I'm just going to take the delta H of that reaction, or the standard heat of that reaction, that was for 2 moles, and convert these grams to moles. Okay, so if I start with 2684 grams ETOH times the molar mass of ethanol, or 1 mole, and then this delta H is for 2 moles, and that's negative 2469.4 kilojoules. And this should be negative 71966 kilojoules. We need 4 sig figs here, so that needs to go in scientific notation, so negative 7.196 or I'm sorry, 7, because this is a 6. Oh, sorry. Yes. And what is it? 10 to the 4th kilojoules. Questions about that at all? So practice using those things like percents, molarity, density as conversion factors. I think we're going to stop at least here for a moment.